Certain basic functions, or sometimes we call them parent functions, that behave a certain way or look a certain way on a graph. And then we can do things to that parent function to either make it skinnier or wider, or shift it around somewhere into a new location on the XY plane. So what would help as you're working through these problems is to be referring back to the set of parent functions that I gave you in a handout that had all the different parent functions on one page, because that'll help you know what kind of shape you're looking at when you see these equations. Now, by looking at g of x here, I can see that x is raised to the power of 2. So the parent function would be f of x equals x squared. And if I look either in the book or on the handout, I would realize that the parent function has, and I'm going to use yellow for the parent function because it's lighter. The parent function would have had a point 0, 0, because if you plug in 0 for x right here, you would get 0 for y. If you plug in positive 1 for x, you would get 1 squared is 1 for y. If you plug in negative 1 for x, negative 1 squared is positive 1. Plug in 2 for x, 2 squared is 4. And then symmetrically, when you plug in negative 2 for x, negative 2 squared is 4. Then we have 3 squared is 9. Negative 3 squared is 9. So this is what the original parent function, f of x squared, looks like. It's a rounded U shape with both ends traveling towards positive infinity for the y values. Now, g of x is a translation of f of x. If we multiply everything, all of the y values are going to get multiplied by a factor of 2. That's going to stretch, this yellow parabola will be stretched to be thinner. Now, what might be easiest to help us see this is if we did a t-table. So for g of x, we're going to do a t-table, and g of x is another way of saying y. So I'm just going to say x and y. Alright, so when I plug in 0, 2 times 0 squared is still 0. When I plug in positive 1, I get 1 squared, which is 1. 1 times 2 is 2. And the same thing happens when I plug in negative 1. When I plug in x equals 2, remember 2 squared was 4, but now I'm going to multiply that by 2 or double it. So instead of 2 squared equals 4, I'm going to get 2 times 4, which is 8. And the same thing happens for negative 2. Alright, so let's plot those points. So we start out at 0, 0, same vertex. At positive 1, I'm not going to, I get to go up, I have a higher point, is what I'm saying. Then I have the same thing on the other side. For 2 and negative 2, 2, and negative 2. Alright, so that's enough points for now, because I can now see enough to connect my dots with the U shape. So this is supposed to look rounded, not pointy. And it's going on into infinity, but it is thinner. It's been stretched, kind of like a rubber band getting pulled upward. So that's stretching. Okay, then we have a h of x. So again, we see the parent function is still going to be the yellow, like it was before, and I'll do that again. So the parent function goes through these key points. Right. And it just helps. I like seeing the original so we can see how the translated version is different from the original. All right, so again, we can do a t-table. We can do x and y, and this will be for h of x, which equals 1/2 x squared, or in other words, x squared divided by 2. So what we're going to do is we're going to take all our original values and cut them in half. So I'm going to put in 0. 0 squared is 0. 0 times 1/2 is 0. Okay, so I'm still at the vertex of 0, 0, same vertex, origin. When I plug in positive 1, 1 squared is 1. 1 divided by 2 is 1/2. All right, so now instead of when I get to 1, I go up here. Instead, I'm only going to go halfway that high for both 1 and -1. So you can already see that it's going to be a wider U shape than before. And then 2 and -2. What's going to happen when I do 2 squared is 4. -2 squared is also positive 4. So cut those in half. 4 divided by 2 is 2. So that happens on both of these. So now 2 and 2, -2 and 2. Let's put in 4. 4 squared is 16. Half of 16 is 8. -4 squared is positive 16. Half of 16 is 8. Right? So 4 and 8, -4 and 8. Right, so now we can make our graph. And you can see that now it is wider. It has been what we call compressed. Sometimes we'll call that compressed. Or you might say that it was stretched horizontally that time. So for g of x, you could think it was pulled. If you imagine a rubber band with a tack in it right at the origin, you could imagine that the rubber band was stretched upward. For h of x, you could imagine that the rubber band was stretched wide. Okay, this one is different from the other two because the coefficient of 1/2 is inside a set of parentheses, and that whole quantity is being squared. Before, the coefficient was not, like for g of x, 2 was not being squared, only x was being squared. Here, 1/2 is not being squared, only x was being squared. But now, there's the coefficient is inside the quantity to get squared. All right, so let's see what happens with that. So again, we'll put our parent function on, key points, 2 and 4, 3 and 9, and then symmetrically okay. So we'll do our t-table, x and y, putting in 0. So put in a 0 right here. 1/2 times 0 is 0. 0 squared is 0. So the origin is still there or the vertex is still at the origin. All right, putting in 1. Well, when I put in positive 1 here, I get 1/2. 1/2 times 1 is 1/2. And then square that, 1/2 times 1/2, multiply straight across, and you get 1/4. All right, same thing's going to happen if I plug in a -1, because then I'll have a -1/2 squared. And when I do -1/2 times -1/2, I'll get a +1/4. So, okay. Now it's harder for me to graph that because 1/4 is kind of difficult to do on, I mean, I could try zooming in. I think I'm already zoomed in as far as I can go. So this would be a hard one for me to, I mean, I guess I could just put it down like this. All right, so let's do 2. If I put in 2 and -2, what happens? Okay, so I get 1/2 times 2 over 1, quantity squared. So 1/2 of 2 is 1, and 1 squared is 1. Okay, same thing's going to happen if I multiply times a -2. I'll have -1. -1 squared is going to become a +1. All right, so let's see. At 2, I'll have +1. At -2, I'll have +1. All right, let's go to 4. So if I plug in 4, I'll have half of 4 is 2, so I'll have 2 squared, which is 4. And likewise, if I put in a -4, then I'll have -2 squared, which is still +4. So at x equals 4, I will have a height of 4. At x equals -4, I will have a height of 4. And I think that's enough. I'm just going to go ahead and try to estimate the rest of it. All right, so you can see how that, what happened there is again, it's being stretched horizontally, or you could think of it as being squashed vertically, because it's, yeah. All right, so notice that having a 1/2 on the outside of x, that squashed it down, but not as much, right? Because the denominator of 2 was not being squared. So there was a slower, or a less of an effect making it stretch horizontally. Here, when it was inside with the x, that squashing effect is more intense or stronger for each step. What else could we do? I think we should do, I'll make up a part D here because I think it's worth experimenting a little bit with looking back at g of x. Let's make this one, what am I on, j of x? Let's make j of x, let's put the 2 inside with the x and see what kind of effect that has. So I'm trying to readjust my screen because that's kind of low for me to write. Oh, maybe I could just move it up. Hello. There you go. Now we're cooking with grease. So I don't know if I'm gonna, let's see, x, y. Okay, so now I want to do 0. Again, if I plug in 0 here, 2 times 0 is 0, 0 squared is 0. Plug in a 1 and a -1. 2 times +1 would be, 2 times 1 would be 2. 2 squared would be 4. Or if I put 2 times -1 quantity squared, that would be -2 squared, which would also be +4. So 4 and 4. All right, so I'm actually going to use blue to do this one, and I'm going to do it here with the g of x so you can see the difference. So I just had, what did I have? 0.0, 0, 1 and 4, and -1 and 4. Okay, so again, we still have a vertex at the origin, but now instead of with the parent function, I would have had 1, 1, or with g of x, I would have had 1, 2. Now I have for k of x, which is 2x quantity squared, I will have 1 and 4, and negative 1 and 4. And so you can see that this thing is going to be stretched much more intensely than the purple, because that 4 is being exponentially increased at a higher factor. Okay, fun stuff, right? So that's vertical stretching and shrinking. Okay, so look at these two gray boxes. The top box says vertical stretching or shrinking. The second box says horizontal stretching or shrinking. All right, so vertical, looking at the top box again, notice that the coefficient is outside of f of x, and for the second box, the coefficient is on the inside of f of x. It's part of the input. All right, so that's what we were just messing with here, right? We were seeing that g of x and h of x had the coefficients outside of the parent function, the original parent function, right? They were not part of the input. And when we have that, we call that vertical stretching when the coefficient is greater than 1. And we call it vertical shrinking when the coefficient is between 0 and 1. Down here, with the coefficient being part of the input on both C and D, we will call that horizontal stretching, right? Because it got wider. And for D, which the picture is actually up here, the blue part, notice that D got in the horizontal direction. If you could just imagine bringing your hands closer together in front of you in the horizontal direction, you would be squashing the parabola in to make it more narrow. So that's why we would call this a horizontal shrinking. Or I like to say compression, but this is the terminology they're using in this book, and it works. Right, so that's what those two boxes are all about, and they break it down formally. So you can see it says if the coefficient is greater than 1 and it's on the outside of the function, then we will call that a vertical stretch. And if the coefficient is a fraction between 0 and 1, it's going to squash it vertically, a vertical shrinking. And when we have the coefficient on the inside, it'll be pulled apart horizontally, so we'll call that a horizontal stretch. And if that's when your coefficient is a fraction between 0 and 1, you get a horizontal stretch. And when your coefficient is greater than 1, it'll have the effect of squeezing and cause a horizontal shrink. Okay. All right, then we have reflecting. So we looked at shrinking and stretching, and then we have reflecting. So I'm going to stop here just so this video doesn't get too long and start a new one.